This next property is similar to our exponential function property, which said if we had the same bases of our exponents, right? If we had b to the x equal to b to the y, then that was true if and only if x is equal to y. Same idea here, except for now we need the same bases for our logarithms. So same base logarithms comes from these two x and y being equal to each other. And that works backwards as well. If we have the same base, and that means x has to equal y. So we see, for example, here, log base 2 of x is equal to log base 2 of 6. Since they have the same bases, then we know x is equal to 6. Over here, if we know e to the y is equal to 2, then if you plug those into any logarithm, and if you have the same base on both sides, so ln obviously is the same base as ln, then we know that ln of e to the y has to equal ln of 2, because we know e to the y is equal to 2. This could have been, I could have done log of e to the y is equal to log of 2. So knowing this little fact here can create lots of different logarithms from that. Alright, so we're going to do our first example here. And what this property is showing us is if we can get this to simplify to only one logarithm on this side, and if it has the same base as the logarithm on this side, then we can go ahead and solve for x. So on the right hand side I have two logarithms. They have the same base and they're being subtracted, so my quotient property tells me that I can take 10 and divide it by x minus 4, and I still have log base 2 of 5 on the other side. Now I just have one logarithm on each side with the same base, therefore 5 has to equal 10 over x minus 4. I'm just going to go ahead and multiply by x minus 4 now. That's going to give me 5x minus 20 is equal to 10. 5x is going to equal 30, and so x has to equal 6. And that is our solution here for part A. Let's take a look at part B here. We have log base 5 of x squared plus x equal to log base 5 of 20. Notice that we already have the same base on both sides, so by the one-to-one property, I can go ahead and set x squared plus x equal to 20. To solve for x here, I see that I have all the makings for a very nice quadratic. All I have to do is subtract the 20 to the other side, and this will then factor to x plus 5 and x minus 4, and that gives me x is equal to negative 5 or 4. Okay, last problem here. So we have log base 3 of 15 is equal to log base 3 of x plus log base 3 of x minus 2. Go ahead and give this video a pause, see if you can try this problem on your own. Okay, hopefully you paused that and gave it a try, and let's go ahead and just do it together now. We need to combine these. They're being added together in the same base, so the product property tells me I can go ahead and multiply these, so that really gives me x times x minus 2. The one-to-one property tells me that since they are the same base, I know 15 is going to have to equal x times x minus 2, which I'm going to go ahead and just distribute, gives me x squared minus 2x. And again, we've got this quadratic going for us. I'm going to subtract the 15 over, and so this is going to factor into x minus 5 times x plus 3. So I get x is equal to 5 and x is equal to negative 3. So one thing I actually forgot for us to do in part B is to check our solutions, because when we get two values, we always want to double check and see if maybe we got an extraneous solution. So I'm going to take both of these and just plug them in over here to these x's and then see what that gives me. So let's start with 5. I have log base 3 of 15 on this side, log base 3 of, that's a 3, of 5, plus log base 3 of 5 minus 2. So this, we'll keep it like that. We'll simplify. 5 minus 2 is 3. The product property still works here, and lo and behold, 5 times 3 gives us 15. So see how it's the same thing? So that means that 5 is a good solution for this problem. Let's go ahead and check negative 3 and see if that works. So we'll do the similar thing here, except for I'm going to plug in negative 3 here and there. And so we get log base 3 of negative 5. And wait a minute. Remember, we can't even plug in negatives to a logarithm. So this right there is already just telling us that negative 3 is not a solution to this problem. Therefore, our only solution is 5a in this problem.